Hiya! So in this video, we're going to go over a example of a Poisson scatter. Um, Poisson scatter. That's it. A Poisson random scatter, I guess technically. Okay, so let's kind of look at this. First, let's set up the story, the example. So here we're living in a fancy house. So we's rich, girls. We rich. I hope you're ready to spend that money because we rich. So we have a pool. That's what makes us having a fancy house. So if you have a pool, you live in a fancy house, and remember to invite me for summer. But the problem is we're not rich enough to actually clean the pool during the winter because it's Canada. Actually, do people have pools in? Anyway. Um, so basically, when summer hits, well, you go to like look at it and there's bacteria growing. Like obviously, like you haven't done anything for a whole winter. Theoretically, the ice, I don't know what happens with the water. Anyway, you left it there for a while and now there's bacteria. Point is, there's bacteria in the water. I don't actually know if this works in Canada. It works in California, but in a volume, so basically, if we look at the pool, in every 1,000 drops, so here we're thinking 3 dimensions, in every 1,000 drops, there's roughly 2,000 bacteria. So that's a lot of bacteria, which are all separate from each other, right? You can't have two bacteria all on top of each other, and they're roughly randomly located, right? They're all doing their own thing. So we can basically use our theorem from before in order to look at this thing. Now, we have a big fancy house, we have a pool, and we have bacteria. So obviously we love biology. So rather than like throwing chlorine in there and trying to kill all the bacteria, we're gonna go in and actually grab some of that. We're gonna take a single drop, and we're gonna smear it uniformly on the surface of like a little petri dish, right? And since we're totally enamored with the bacteria, we're gonna actually give the bacteria some food so it can grow, and we're gonna put it aside. We come back a few days later, and we see nice, healthy colonies of bacteria. Now, what's a colony of bacteria? Well, it's wherever there was one bacteria, it started to grow by itself, right? And that is where a colony is. So the number of colonies basically tells me the number of bacteria I had on this plate from the beginning. And the question is asking, what is the distribution of the number of colonies over the whole plate and over an area of half the plate? So let's kind of look at some of these points. So I have 1,000 drops, gives me 2,000 bacteria. I take out a single drop and smear it uniformly over the surface of a dish. And we want to know number of colonies over the whole plate and over an area of half the plate. Notice how there's not actually that much information. There's a lot of words, but there's not that much information here. So let's kind of break this down and figure out what we're kind of doing. So first, I know there's 2,000 bacteria per 1,000 drops. So 2,000 bacteria in 1,000 drops. So what this means is we expect roughly 2 bacteria per drop, right? That's kind of what we would expect. So if we take 1 drop out, we expect about two bacteria in there. If we then put them on a dish, we'll have bacteria probably in 2 different locations because we expected to, which means in this case, remember expected, this should hint at this is our mu. Mu is equal to 2. And so we have a Poisson distribution with 2 here. And this is giving us the whole plate. So, and that's basically it. So the number of colonies is just 2. So here you have to just kind of think about this. So the first answer is equal to 2, number of colonies on whole plate. Right? Okay, so how about half the plate? Well, if I look at any half the plates, they're going to be in random locations, right? I don't know where I smeared them, so I should probably get half. So half the plate implies mu over 2, so it's about 1. So these are the 2 main things that we kind of had. And I should have done this below. Can I just move all this below? Yeah. Oh, oops, no. Go back. I apparently grabbed too much of this. Can I just do... no, stop. This. I want just this part. There we go. Hopefully this is enough room. Almost. Can I just grab... Nope. Okay, so we're going to put it here. Okay, so that kind of answers the first two things. Now what we're going to ask is we're going to suppose that there's a probability that each bacteria that I put onto my thing, well, maybe they're not going to eat the food, or they're just going to, it's going to be too hot or something, but there's a probability P that they die. Like they're not, like there's a lot of things that happened. So there's a probability P that they all die. And so this is where we're going to be using our random scatter theorem. And we're going to ask, what is the distribution of the number of colonies on the entire dish? So, okay. So what we know is we already know the intensity from before, right? We already know that when we scatter it, we should have lambda is equal to 2 is our intensity. Okay? And we want to find the probability of having one particular colony on our dish. So how do we kind of do this? Well, we take some area. So in essence, what we're going to do is first we're going to take an area that's small enough. So let B be small enough. That it contains exactly one colony. B be small enough that it contains exactly one colony. So in other words, what I want is the probability of one bacteria in B to be roughly equal to 2 times the area of B. And I want the probability that 2 bacteria B in B be equal to 0. It'd be roughly 0, right? So what we end up having is we're going to have to multiply these by P. So what we end up having is the probability... Do I have room in the next page? A little bit. What we end up having is the probability of one colony in B. Notice how here the word changed, right? I no longer have bacteria, I have colony, right? Because there's a chance that they might die. So this is just the sum over all these things multiplied by the probabilities. So you have one bacteria in B and colony forms plus 2 bacteria and colony forms. I'm running out of room, which is why I'm not writing fully. These are independent, so basically what we end up having is 2 times the area of B times P. So here we have colony forms gives me P. 1 bacteria in B gives me all of this. And on the other side, I have 0 times P. So this basically comes to 0, and I end up getting 2 times the area of B times P. Now, let's kind of go back and let B be the entire dish. And we know that B has unit area, so we just took like, we're just going to assume it has unit area. That means the area of B is just 1. So what this means is that we know that the scatter has intensity 2 times P. So if B is equal to 1, if area of B, 1, what we have is the scatter of colonies has intensity 2P per unit area. And the total number of colonies, and this implies the total number of colonies on the whole plate has a Poisson distribution with parameter 2p. And that's basically it. So basically the example is actually what is known as a thinning of a Poisson scatter. And basically the reason why this is called that way is because if you think about it, is we start off with a Poisson scatter with intensity lambda, and each point has a probability p of staying alive. And so you're kind of multiplying these together out to have some less number of things. And so you're just going to have an intensity lambda p at the end of this. And so here the intensity is basically giving us the parameter for the distribution. So it's kind of nice. So we're going to stop here in this video. Since we have a little bit more time, in the next video, we're actually going to talk about continuous distribution. So we're going to start talking about that a little to start getting people ready for integration and stuff. So that's it for the discrete stuff, and I will see you in the next video for continuous. See you then.